Hello friends, today we'll be learning about quicksort. Before starting to learn any topic in any subject, you should know why are you learning it and what is it what you're learning. How is always I think how is always the very easiest thing, but if you know why are you learning it and what's the use of it, it will make things more interesting for you. So before starting, you should just figure out, find out, ask, but you should know that why are you learning it. So we are learning about quicksort today, but why are we learning quicksort? What's the need of quicksort? Sorting, we all know quicksort is a sorting method, and we all know sorting is required for most of the tasks. We need sorting. I don't need to go deeper why we need sorting. Sorting is needed. But what is different with quicksort? Why should we learn quicksort? Quicksort is considered as one of the most efficient sorting method. But how and why? Let me give you an example. A sort function, inbuilt sort function you might have used. If you have not used, that is fine. Most of the programming languages provide you sort function, which is inbuilt. Like C++, Java, Python, these languages provide you an inbuilt sort function. That sort function is highly optimized. If you'll write your own sort, it will be mostly the case that it won't work as efficiently as the sort function, inbuilt sort function. That inbuilt sort function is implemented in quicksort and merge sort, some combination of quicksort and merge sort. We don't need to go deeper how is that implemented, but that is implemented in some combination of quicksort and merge sort. So we can say, yeah, quicksort is the efficient algorithm. We need to learn it. Spoiler alert, I'll be telling you a question which had been asked in Facebook like 2 weeks before, and that can be solved using the same method which we'll be going to use in quicksort to sort the array. So same method can be used. Stay alert and we'll discuss this question at last. That is a very easy question, but it's asked in Facebook. So yeah, it's important. Now we know why should we learn quicksort. But what is quicksort? Quicksort is a sorting method which uses divide and conquer method technique. What is divide and conquer technique now? Divide and conquer technique is we have a problem. We divide this problem into multiple subproblems. We solve these subproblems recursively, get the result, and consolidate the result. But why are we just dividing the problems into subproblems? When I was in my BTech, when I was learning these things, it was the most confusing thing for me. That divide and conquer, why are we dividing these problems into subproblems? It's fine. This question comes in our mind. It's totally fine. We'll be looking at the quicksort solution, so that question will also be solved for you. You'll get the answer for that question. Stay tuned. And it is a comparison based sorting algorithm. There are non-comparison based sorting algorithm also available like radix sort, bucket sort, and mostly you might have heard only about comparison based, which is bubble sort, insertion, selection, merge, quicksort. All these are comparison based sorting algorithm. When we compare two elements of the array and take decision whether to swap it or not, take decision accordingly. It is an in-place sorting technique. In-place is we don't need any extra space for sorting. Like in merge sort, we need extra space. If you don't need no merge sort, it's fine. In quicksort, we just don't need any extra space for sorting. Its space complexity is of 1. That make it most efficient. Obviously, it's time complexity and method also. But yeah, this is also one of the feature that it is in-place sorting technique. Let's move to how do we sort an array using quicksort. Let's take an example first. This is our unsorted array, and this is the result what we want. The main heart technique of quicksort is we take a value, we find the correct position of that value by putting all the lesser values to this value to the left and greater to the right. The value which we have taken, we call it as pivot. So what we do, we take a pivot and all the values which are less than to pivot, put it at left side, and all the values which are greater than to this pivot, put it at right side. And which all the values which are equal, you can put it at either side. It's up to you how you are implementing the quick sort. It's fine. So in this example, let's take our pivot as 3. We have taken the pivot as 3. Which all values are less than this? 0, 2, 1. It can come in any combination at left and right side, but all the lesser values will go at left side and all the greater values will come at right side. That is fine. That is true, but it can either be in sorted way or non-sorted. That's fine. It doesn't have to be in sorted manner. It can be in unsorted manner also. 4, 7, 5, 9. Now we have put all the lesser values to left side and all the greater values to right side. This value is at its correct position where it will be going in the sorted array. Now what we can do, we can divide this problem into 2 subproblems where we have to sort this array and this array. These can be sorted independent to each other, because none of these values will be going in this place and none of these values will be going in these indexes. And this value is already at the correct index where it should be. Now we are dividing this array into 2 subproblems. As we have discussed, we'll divide this problem into 2 subproblems and recursively we are going to solve that subproblem. Now our problem is we have to solve only this. We have to sort only this array. How are we going to sort this array? Take one pivot again. We have taken this pivot 1 and put all the values lesser to the left and all the values greater to the right. Now again divide this subarray. One is left and another is right. This value is already at its correct position. Now do the same thing in these arrays also. This array is of size 1, so we don't need to do anything. It is already sorted. If it's size 1 or 0, it's already sorted. This array is also size 1. This is also already sorted. We don't need to do anything. So our left side is sorted. Now we need to sort this array with same way. Recursively take a pivot, put all the values to the left, all the lesser values to the left or the greater values to the right, and then partition it. Nothing else we need to do. Once we have got the correct index of the pivot, just partition these arrays to 2 parts. One part is lowest index 2, this index minus 1, whatever is the index of pivot, and another partition is index plus 1 to highest index. Okay, we can just solve it recursively in the same manner. I think it's clear now. Now that question might have also been cleared for you that why do we use divide and conquer. Look how easy it made the solution. It made sorting very easy, isn't it? Okay, so now the main part comes. If we can put all the values to the left and right, we know how to solve it. But how to do that? How do we put all the lesser values to pivot to the left and all the greater values to the right? That's the main heart concept of this quick sort, that putting all the lesser values to the left and all the greater values to the right and then partitioning it. This is called partitioning. So how are we going to do that? For this, we'll be taking let's take 2 variables, start and end. This last variable is our pivot, so end will start from last minus 1. What do we need? All the lesser values to the left and all the greater values to the right. So what are we going to do? We are going to search opposite thing. From the left, we are going to search the greater value, and from the right, we are going to search the lesser value, and then we are going to swap it. Using this, what will we get? All the lesser values to the left and all the greater values to the right. In this example, we'll see. Move from left to right for the start. 0. Is this greater than 3? No, it is not. Move forward. 4. Is it greater than 3? Yes. Then stop here. It shouldn't be at the left side. If all the values ahead than this are greater, then it's fine. If not, we need to swap it. Okay. So stop the start here. Now our start is at this position. Let's start from end. End is at position this and value is 1. Is 1 less than 3? Yes. Then what we need to do? Obviously swap it. Now our new array is 0, 1, 2, 7, 5, 9, 4, 3. Again start the same thing from the same position where we have left. Is 1 less than 3? No. Is 1 greater than 3? No. Move forward. Is 2 greater than 3? No. Move forward. Is 7 greater than 3? Yes. Then we are going to stop here. Is 4 less than 3? No. Is 9 less than 3? No. Is 5 less than 3? No. Is 7 less than 3? No. Is 2 less than 3? Yes. Then stop here. Our end is reached here. Do we need to swap this? No, because our start is greater than end. If start is greater than end, we don't need to swap because it is already lesser and at the left side. So we don't need to swap. And when our end is less than start or start is greater than end, it means we have got the correct position for this pivot. Swap this pivot with the start. Now our array is 0, 1, 2, 3, 5, 9, 4 and 7. Now we have got this index position from where we need to partition. Left side of it is all lesser values and right is greater values. So just partition it. Its index is 3. Partition it from 0 to 2 and 4 to 7. Now we have got two new arrays. Do the same partitioning and then run the quicksort on both the sides. Run the quicksort on both sides using same method, partitioning and then running the quicksort on both the sides. I think it's clear. Algorithm is clear. Let's look at the pseudocode now. If you have any doubt, you can ask me in the comment section. It's very interesting. It might be a bit confusing. So just let me know if you have any doubts. Now we'll be moving forward to the pseudocode. What we need to do? We just need to run this quicksort. If our array size is greater than 1, we need to run this quicksort. If our array size is less than equals to 1, we don't need to do anything because it's already sorted. So that's what we are checking here. If our array size is greater than 1, we need to partition and then run the quicksort on both the sides as we have discussed. And for running the quicksort, what we are doing, we are first taking the pivot as high value, highest index value, then start and we are initializing start and end, and then running this loop. In this, what we are trying to do, we are just moving forward until we get ARR of start is greater than pivot. This is a bit mistake. Until the ARR of start is less than pivot, we just need to move forward. When it's greater than or equals to, we'll stop there. Same we are going to do at end. We can use equals to here also. That when it's equal, we don't need to do anything. So you can add equals to here and here also. It's up to you how you want to implement. It's fine. When we have got the start and end index, if start is less than end, then swap. If it's not, then just break because we have reached to the end. We have got the correct position. Then swap the error of start to the error of high, which is our pivot value, and return the start index. You can try run it. You can try running the. You can try writing the code and running it, and see if you get any problem, any issue. Let me know. It's fine. Now let's come to the time complex. I'm not going to explain much about time complexity. It will become a bit confusing. Time complexity of quicksort is n log n for the average and best case. For the worst case it is n square. In this case, worst case can happen when the array is sorted in ascending or descending order. Okay. Now few things to discuss now. That how can we overcome this worst case? This worst case is coming when our array is sorted in ascending or descending order and when we are taking the pivot as high. It's up to us. Whatever value we can take, we can take as pivot. It can be either high value, highest index value, or lowest index value, or medium value, or any random value. So if we take this randomized approach, if we are taking the pivot as random value, this chances of the worst case happening becomes very low. So best to take as random value. Okay. Now to the question which I was saying in the starting of the video that we are going to discuss. The question is, we have given an array. It can be anything, positive, negative, 0 values. Array is 7, 5, 0, 2, 9, 0, 6, 0, minus 4, minus 2, 0. So this is the array given to us. What we need to do, we need to put all the 0 values to the last. And we don't need to maintain this indexing, this ordering of the other values. We just need all the zeros values to the last and non-zeros values to the beginning. How can we solve it? Same concept, start from the starting and ending. Whenever you get any value which is not 0, like in this here, you got the value which is non-zero. Iterate from the start. Whenever you get any value which is 0, just swap it. 7, 5, minus 2, 2, 9, 0, 6, 0, minus 4, 0, 0. Again start searching for the value which is non-zero. Minus 4 we have got. And from here start searching for the value which is 0. This is 0. Now swap it. Our array is 7, 5, minus 2, 2, 9, minus 4, 6, 0, 0, 0, 0. Start searching for non-zero value. This is this. And for the start searching for the 0 value. Start is greater than end. We don't need to do anything. We have got the result. We have got all the zeros values to the last and all the non-zeros values to the right. Look, it's very easy. But the quicksort method the method which we used in quicksort, this made it very easy. Otherwise, we would have needed some extra space or anything. But this is the easiest way to do this, solve this question. Thanks for watching. Thank you.